And let me just remind you of a setup that we have discussed before. So we fix K and mu, a pair with K, a compact Hausdorff place. And mu, a finite Borel measure. Then we consider L infinity, a family of operators on L2 of K mu, defined as MFG is FG, where F comes from L infinity K mu and G comes from L2 K mu. And we've seen that L infinity is its own bicommutant, so hence it's a von Neumann algebra, and it's fairly clear from the definition that it's an Abelian von Neumann algebra. There's a thing that I'm going to need in the proof that is coming up, and so in order to prepare you for this, let me mention this right away, because it's sort of a non-trivial fact that I'd rather not prove. So let me be upfront about it. There is a relatively detailed proof in the in the book. So note that with C written as the MFs, where F is in C of K, we get a subalgebra of L infinity. We claim that C is weakly or strongly dense in L infinity, or in other words, the bicommutant of C is L infinity. Right, so the claim that I'm coming with here is that if we look only at those operators that you get from taking a continuous function on K, that of course is different from L infinity, because L infinity is much more flexible. You're allowed to multiply on with any function. It just has to be measurable and bounded almost everywhere. But of course, an example of a measurable and bounded almost everywhere function is a continuous function. Right? So, and what I'm claiming is that that subalgebra is going to be dense in the topologies that we use to define what it means to be a von Neumann algebra. And the way you prove this is that you realize, this is done in the book, you realize that the weak operator topology is the same as the weak star topology that you get on L infinity by considering it as the dual of L1. And then you prove that the continuous functions are weak star dense in L infinity. And you use this by, you do this by using that it's a Borel measure, right? This is an important assumption that I made. So being a Borel measure means that any measurable set can be approximated from within by compact subsets, and from outside by open subsets. And using that, you can sort of take a function, say an indicator function for a measurable set, and you can approximate that in in the weak star topology by a continuous function using sort of Tiz's extension theorem or something like that. Right, so that's, I'm going to have to use it at a critical point in this proof, and so I don't want to be saying things as I'm pulling rabbits out of the hat in a very late stage in the proof, but I'd rather not prove it because it's technical and not very interesting, so at least I'm stating it up front, right? So I will just say this is a claim, and you'll see that I desperately need it at the end of this pencast. Okay, so now I'm ready for my theorem, and in a sense it is a very satisfactory theorem, but it has an assumption, namely I'm going to ask for a cyclic vector, and that is a very strong assumption, and we're going to talk about how to remove that assumption a little bit down the road. But here goes. So let A in B of H be an abelian von Neumann algebra with a cyclic vector x in H. So this is a non-trivial assumption that we will talk about removing later. Then there exists k mu as above. So k is a compact set, mu is a finite Borel measure on k, and a unitary u, which is a bounded operator from H to L2 k mu. So that u of A of u star is L infinity sitting inside B of L2 k mu. So let me just note something about what it is that we're talking about here, right? So the setting is that I have H, which is my abstract Hilbert space on which my A acts, right? So if I have an element in A, it's an operator that goes from H to H. And so the statement is that I can replace H by an L2 space, L2 k mu, in such a way that these two Hilbert spaces, H and L2 k mu, are the same Hilbert space, right? What does it mean for two Hilbert spaces to be isomorphic or be the same? It means that there is a unitary between them, and this unitary I'm calling U, right? So it goes in this direction here, maybe in a different color. Let me talk about U star, which goes the opposite way. Right, so these Hilbert spaces are the same. Of course, it's very easy for two Hilbert spaces to be the same. They just have to have the same size of an orthonormal basis. But nevertheless, that's what I'm talking about with U. Right, and then the claim is that inside L2 k mu, we have some operators. Right, some of these operators. Among these operators you might want to consider are the ones that we call MF that lie in L infinity. Right? And then the claim is that whenever I take that this unitary, in a sense, will transport all of A all the way over to L infinity. Right? So whenever I have an operator T, then if I take T and I compose it with first U star, maybe I'll use colors like this. I compose it first with U star, and then I use T, and then I compose down with U. Then the claim is that I get something that comes from L infinity. right? So the statement is that I can find a unitary that transports my abstract von Neumann algebra A into a concrete von Neumann algebra, namely L infinity, which lives on L2 of K mu. Right, so this is the statement. So this is sort of the idea of U. Let me point out that this kind of way of moving a whole operator algebra from one Hilbert space to another Hilbert space is a very strong thing. Right? So in this situation, let's write perhaps phi from, it's a map that goes from B of H to B of L2 K mu, defined just like this, right? So phi of t is just U T U star, right? So I'm taking the map that takes an operator in B of H and sends it to an operator on L2 K mu by simply composing with U and U star in the only reasonable way. So this is sometimes called a spatial star isomorphism. So, I mean, it's clearly a star isomorphism because it respects all the operations that we have in B of H, thinking of B of H as a C-star algebra, because U is such a nice map, right? So, for instance, Y is phi of T1, T2. What is that? That is U of T1, T2, U star. But what is phi of T1 times phi of T2? It is U T1, U star, U T2, U star. But U is a unitary, right? So this cancels out, and that's the same. So it's a special kind of star isomorphism between two C-star algebras that happen to live, both of them, on a Hilbert space. And what's nice to note is that that phi is obviously, I'm saying, weak, or strong, continuous. Just because, checking whether things can converge in the weak topology, this is something you do by taking the inner product and seeing what happens. But when you apply phi, you will just move things around with U, and U does not really change the inner product. That's the point of the unitary. So that's why this is such a nice conclusion in the result, that not only am I claiming that my abstract von Neumann algebra is star isomorphic to L infinity, I'm claiming that it's spatially isomorphic to L infinity. So that's stronger in a sense, right? So, I mean, I could also say that it's true that, maybe I'll write that. So it is true that A is isomorphic to L infinity as C-star algebras, because the map that I just called phi is a star isomorphism, but the conclusion here is much stronger because we remember the way that they sit on the Hilbert space. That's somehow the point. Okay, so how do we prove this? So that is actually a very pretty proof, which is somewhat visual. So I'll try to make a drawing of how this works. I hope I can make this work in my pencast. So let me, down here I will draw A. Right, so what is A? A is an Abelian von Neumann algebra that happens to live on some Hilbert space. Well, forgetting that it lives on some Hilbert space, it's an abelian C-star algebra. And an abelian C-star algebra has a Gelfand transform onto C of k for some compact space k. So this is already where my k comes from. I can check that off. K will just be the maximal ideal space of A. So we're using the Gelfand transform. Now, I want to also build mu, my Borel measure. And I'm going to get that, you can probably guess, from the Riesz representation theorem. But to be more precise, I'm going to start by defining a map like this, which is going to be a state. And that state I'm going to call phi x. What is the state? Well, phi x of t is going to be the inner product of tx and x. Right, so this is clearly a state. It's a positive linear functional that goes from a to c. And I'm using here that my x, recall that x is cyclic and, as we've seen, also separable. Separating. So this is the x that I'm going to work with. By the way, if x is not already a unit vector, we can rescale it. It's clearly not 0. So let's assume that it has norm 1. I need that in order for phi x to be a state, right? Because a state has to send the identity to 1. So the norm of x has to be 1. So I took care of that. Okay, and then I will define a map psi, defined as phi x composed with gamma inverse, so that map psi lives here. And you can see I just defined it. I mean, we know that the Gelfand transform is an isomorphism, so there's something called gamma inverse. So I'm just defining psi to be whatever you get by starting at C of k, going back to A and down with phi x. Right, so note that this is, so maybe I'll explain that here. So mu is got by Riesz on psi. What do I know about psi? Psi is a linear functional that lives on C of k, and furthermore it's a positive linear functional, right? Because we know that if we have a positive function on C of k, then maybe I'll write that here. If I have f, which is a positive function, except I'll choose a color for it, blue. So if I have f, which is a positive function, then if I send it over here with gamma inverse f, that's going to be a positive element in A, right? And if I have a positive element and I apply a state to it, I will get a number which is positive. Right? So my map psi, which is defined to be a functional on C of k, is actually better than that. It's positive functional, so there is a positive measure which represents psi, right? So psi is actually going to be something that I get by integrating up against mu, right? So what I've obtained now is my set and my underlying compact Hausdorff space and my Borel measure, but now of course we need to go hunting for the unitary that I've promised you as well. Okay, so how are we going to get this unitary? Well, I'm going to define mx, as I've done earlier, to be tx with t in A. Right? So this is something that lives inside H, and it is dense because we have assumed that x is a cyclic vector. Right? So what I have here is mx, and I'm going to define now a map which I will call u naught, that goes from mx to c of k. So that's defined in this direction here. How am I going to define it? Well, u naught of tx is going to be the Gelfand transform of t. Okay, so this is the map I'm calling u naught. Okay, so it's fairly easy to get lost in all of this, but let me just point out what's going on. Right. So how do I define u naught? Well, I say I will take a vector of the form tx, and I'm going to apply u naught to that vector. The way I do that is that I peel off the t. When I peel off the t, I end up over in A. And then when I end up, so that means I end up over here, right? And then I take gamma on that element in A, and I end up in C of k, which is where I want to end up. So this is a really strange definition. The reason why it works is that we have a separating vector. Because it's a separating vector, we know that if tx is the same as sx, where t and s both come from A, then t and s have to be the same. Right? So actually, if you know what t does to x, you know t. So this is a very unusual situation that tells me that I can actually well define a map where I send tx to something that depends on t only. Right? But that's because I have a separating vector that tells me that the map that sends t to tx is an injective map. Right? So my u naught actually makes sense. It's a well-defined map. It's also easy to see that it's linear. And now what we have to do, which is going to take a little bit more work, is that we're going to say, well, mx lies inside H as a dense set. And ck lies inside L2k mu as a dense set. And now the plan is to define u by extending u naught. Right, so this is the setup. So okay, let me try to help you visually a little bit with some colors. So this is somehow, I mean, this is all a lot of things to take in, right? So I have my phi x defined by the standard way that we create state by taking inner products. My map psi was just defined by sort of extending phi x over the Gelfand transform. And now my u naught is the map that we defined in this sort of strange way. Now, how are we going to move on and well define u? Well, it's sort of straightforward what we want to do now, because I have a map u naught which is defined on a dense subset of H, mapping into a dense subset of ck. So to extend it to a unitary, to extend it to a bounded operator from between the Hilbert spaces, I just need to know that it's bounded, and then I can extend it by the fact that you can always extend any uniformly continuous map, which it would be in this case, automatically. So I really need to see what happens when you apply u naught to t of x, the way that this is defined. What happens to the 2 norm of this vector? All right, so I'm studying this map here, and I'm trying to see if it might be an isometry. Because if it's an isometry, then I have a really good shot at extending it to a unitary. That's the idea. So how do we check if it's an isometry? Well, we will just do a computation. So what is the definition of this? So by definition, u naught tx is just the Gelfand transform of t. So I'm talking about the squared 2 norm of that. Maybe I will try to keep this as compact as I can. So what is that? That is the integral of over k of gamma of t absolute value squared d mu. But going on until the next line, this is the integral over k of, so gamma t's norm squared is just gamma of t star t d mu, right? Because I'll do that as an aside here. So gamma of t's absolute value is gamma of t bar gamma of t. And since the Gelfand transform, as we've seen, respects stars, this is gamma t star, gamma t, and that is gamma t star t. So that's where this comes from. So continuing on down here, what is this? Well, we've seen that integrating up against mu is the same as using psi, right? So this is psi of gamma of t star t. But what is psi of gamma? Well, psi is phi x composed with gamma inverse, composed with gamma of t star t. So these cancel out. And so I just get phi x of t star t. And what is that? That is the inner product of t star tx with x, which is txx, which is the norm of tx squared. Right, so reading from the beginning here to the end, you can see that u0 is in fact an isometry. Right? It will take a vector of the length of length tx to a vector of length tx as well. Right. So what happened here is, I really just traced through the definitions. So I mean, it looks complicated, but I just used the definition of what it means, what is the length of u0 tx, and then at a crucial point, I'm using that psi and the L2 norm are intimately connected, because I used psi to create the mu measure, and so that means that I can use psi to compute the value of the norm of gamma t star t, and then the way that psi was built using phi x and gamma, things cancel out, and I end up with phi x of t star t, which is clearly the norm of tx. Right. So this is somehow the key setup. So this shows that u0 is an isometry. It hence extends to an isometry U, right? And I've used now that my x was a cyclic vector, not just separating, in knowing that when I extend from mx to its closure, I actually always extend all the way up to h. And furthermore, note, in fact, U is surjective because U0 applied to mx is dense in L2k mu. So U is unitary. Okay, so that explains now the existence of U. So I now also have my U. So this is part of the data that I promised you. But of course, I'm not done yet, because the claim is that when I apply U to my abstract phenomenon algebra A, I end up with L infinity. So in order to try to convince you that my U will actually move A into L infinity, let's look at a concrete example. We take U, T, U star. Right, so U, T, U star is an operator that starts and ends in L2 of K mu. But I'm not going to apply it to a general element in L2 of K mu. I'm going to apply it to a general element in the continuous functions on K. And the continuous functions on K, since we came up with K as the maximal ideal space of A, these are just what you get out by using the Gelfand transform. So what I'm going to do is I'm going to apply U, T, U star on something in gamma of the form gamma of S, because this is what a generic element in C of K looks like. And the point of doing this is that now I just need to follow the definitions, and you'll see that I get the right thing out. Okay, so what is that? That is U, T, U inverse gamma S, using that the adjoint of unitary is just its inverse map. And you can see that the way that we've defined U as an extension of U naught, we can actually write this as U naught inverse of gamma S, right? Because everything is taking place inside the range of U naught. So it's not just U inverse of gamma S, it's actually U naught's inverse of gamma S. And what is the inverse of gamma S? Well, the way that we defined U naught, the inverse of gamma S is just going to be S applied to X, the cyclic vector. So it's going to be U, T, S, X. Right, so I'm just using the beginning of the definition of U naught this way. But I guess I could write this perhaps in a nicer way as just U, T, S, X. And what is U, T, S, X? Well, T, S, X, when you apply U to T, S, X, that is just U naught of TSX, right? Because I don't need to go all the way to the extension U. I can work just with U naught, because TSX clearly lies in my space MX, because TS lies in A. So what is U naught of TSX? By definition, it's the Gelfand transform of TS. And we know that the Gelfand transform is homomorphism, so that's the same as gamma T times gamma S. Or if you like, it's the multiplication operator that you get from the continuous function gamma T applied to gamma S. So you see this straightforward computation where I sort of move back and forth with the definitions of U and U naught will tell me that we conclude that U, T, U star is the same operator as M of gamma T in the bounded operators on L2 of K mu. So that actually gives me something a little bit stronger than what you might have expected, right? So, and hence that when I apply U to all the operators in A, U and U star, I get all the continuous functions inside B of L2 K mu. That's a little bit surprising because I was aiming to get L infinity and I got C. But but we have seen that U, A, U star is always a von Neumann algebra. Since phi of A is strongly or weakly closed. Right? So the map that I called phi, that is the map that sends all of A into some other operators inside B of L2, that is a map that is strongly and weakly continuous. And its inverse, which has the same form, is also strongly and weakly continuous. I guess that's what I'm using here. So that tells me that when I start out with a von Neumann algebra A, the image of that is also a von Neumann algebra. Right? So that tells me, so consequently, C is its own bicommutant. But we've seen completely generally that the bicommutant of C is the same as L infinity. And so that finishes the proof of what I wanted to prove, right? Because it shows me that not only does any element in A get transferred into a multiplication operator, I also get every multiplication operator this way. But there's something fishy here, right? So I'll just write that as fishy because you might sort of think that there's something really weird going on here, because as a consequence of my argument, C is the same as L infinity. Right? So that tells me that every function which is bounded almost everywhere is a continuous function. I mean, so what I mean there is, of course, not that every function which is bounded almost everywhere is a continuous function exactly, but I say that they are the same except on a null set. Right? And this is actually not wrong. I mean, it doesn't really conflict with anything that I've said, but it tells us that K is a really weird space. Right? So K is a really weird space because it allows lots of open and closed sets. Because I mean, and this is somehow inherent in the approach, because I made K as the maximal ideal space that comes from a von Neumann algebra, and because a von Neumann algebra has many projections, the topological space that I'm creating will have many open closed sets. So it's going to be a very disconnected set. Right? So it's not really, when I'm saying this is fishy, maybe that's a wrong way of saying it. It just says that K has unusual properties. Sometimes this is called a Stonian space. It's the spaces that you get when you represent C-star algebras of this nature. They're going to be weird spaces, right? But it doesn't detract from my result, which says that any abstract C-star algebra that lives on B of H has the form L infinity, provided that I know that there is a cyclic vector. Right? So of course we have to think about that condition, and that's the goal of the next pencast.